Hello and welcome to this Revision Monkey video on what's going to be in the 2022 exams. This video is for the AQA specification and it's for combined scientists, and that's the trilogy version of combined science, which means you take 6 exams at the end of your course, all of which are 1 hour and 15 minutes long. This video covers the major content for Physics Paper 2 and is for higher tier students. So the topics that won't be assessed in this paper are forces and elasticity, forces and braking, and permanent and induced magnetism, magnetic forces and fields. The exam board have told us the required practical to focus on, and this is infrared radiation. I'll put a link to a video covering the information you need just for this required practical, so do look out in the description for that. And they've also told us the topics of major focus for the exam, and these are forces and their interactions, describing motion along a line, forces, accelerations and Newton's laws of motion, momentum, electromagnetic waves, and the motor effect. So this will be the focus of this video, and also look out in the description because I'll put a link there for some practice questions for you on these topics as well. Let's first look at the difference between scalar and vector quantities. Some examples of scalar quantities are speed, distance and time, and some examples of vector quantities are velocity, displacement, force, acceleration and momentum. Now, the difference between the two is that scalar quantities have magnitude only, so magnitude is size, so you can give one of these quantities a big value or a small value, and that will be changing their size. So for example, a speed of somebody could be 5 meters per second, that's giving the size of the speed or the magnitude. Somebody could walk a distance of 10 meters, for example, and that's the size that you give it. Whereas a vector quantity has both magnitude, so the size, and direction. Velocity is the vector quantity which is related to speed. So you'd give, rather than just giving a size like 5 meters per second, you'd also give some indication of direction. So you could say to the right, or in physics sometimes you'll see that they'll put a plus or a minus in front of the velocity as they've given a plus or minus to a certain direction. So if they've decided that everything moving to the right is a plus and everything moving to the left is a minus, they can put that plus or minus in front to indicate the velocity. Displacement is the vector version of distance, and you'll also have force, acceleration and momentum that are examples of vectors as well. So moving on to forces then, we said it's a vector, so we can use arrows to show both the size of the force and the direction of the force as well. So for example, with this falling tennis ball, it will have air resistance going upwards, represented by this arrow, and weight acting downwards, represented by this arrow. The direction of the arrow shows the direction of the force, and the size of the arrow shows the magnitude of the force. So we can group forces into contact and non-contact forces. So some contact forces include friction, air resistance, tension, and the normal contact force. And in these cases, all the objects have to be touching. So friction is when 2 objects are rubbed together. Air resistance, you've got the air particles colliding into an object. Tension, you'll experience that when you pull 2 different ends of material like a rope. And a normal contact force is a contact which is acting at the normal, which is at 90 degrees to the object, which is touching another object. So for example, a book on a table would experience a normal contact force at 90 degrees from the table. Some non-contact forces include gravitational force, electrostatic force, and magnetic force, and in all these cases the objects are separated and don't have to be touching in order to experience the force. Some forces can be measured using a Newton meter, and forces are measured in newtons. So this is a Newton meter. You could, for example, hang your object on the end of this hook here, and that will let you know the weight of the object in newtons, or you could use this Newton meter to pull or push an object and measure forces in that way. Let's have a look at this example. We've got a diver diving off the diving board, and we've got a gravitational force pulling that diver down towards Earth, or we can actually call this weight, because weight is equal to mass multiplied by gravitational field strength. Weight is a force, and it's measured therefore in newtons. Mass is measured in kilograms, so if you ever see it in grams, you would have to convert it to kilograms by dividing by 1,000. And gravitational field strength is measured in newtons per kilogram. The weight acts at a single point known as the centre of mass of an object. So here, for example, in this person, this could be the centre of mass of that person. It's quite difficult to work out for irregular shaped objects where the centre of mass is, but that's where the weight will be acting downwards. On Earth, the gravitational field strength is 9.8 newtons per kilogram, sometimes round up to 10. What is the weight of the diver if he has a mass of 50 kilograms? Well, weight is mass times gravitational field strength. So if we do the mass times by 9.8, we'll get a weight of 490 newtons. Let's look at an example if this diver was on the moon. On the moon, the gravitational field strength is just 1.6 newtons per kilogram. What is the weight of the diver if he has a mass of 50 kilograms? Well, importantly, the mass does not change. Mass is still 50 kilograms, but if we multiply it by 1.6, the diver would have a weight much less of just 80 newtons. So the key thing is your mass, wherever you are, does not change. However, your weight, because in physics weight is a force, we're not talking about mass in kilograms. When we're talking about weight in physics, we're talking about a force in newtons. So really it's important to say that your mass is, you're talking about your mass when you step onto some scales rather than your weight, because in physics weight is the force with which you're pulled towards an object. So that's why on the moon your steps will be a lot lighter and a lot bouncier, because there's less of a gravitational field strength pulling you towards the moon compared to the Earth. So important, mass stays the same wherever you are, but your weight can change depending on the gravitational field strength of the planet you are on. Looking at resultant force then, you can think of the resultant force as the overall force acting on an object. So when you take into account lots of different forces, what's the overall force? So if we look at this block here, we have 5 newtons pulling to the right and 2 newtons pulling to the left. So the 2 newtons pulling to the left, we need to take away from the 5 newtons on the right, and we would have an overall force of 3 newtons. And because force is a vector, we'd have to tell the examiner the direction that that box will move in as well. Because there's more newtons pulling it to the right, overall it would be pulled to the right. You might also get an example where there's multiple forces acting on an object. For example, if it's still 5 newtons pulling to the right, but in this case we've got 2 newtons and 3 newtons to the left. Overall on this side there'll be 5 newtons pulling it to the left and 5 newtons to the right. So 5 minus 5 would be 0 newtons. So when there's 0 newtons, there is no resultant force, or it's better to say no overall force, and the resultant force is 0. There's a little bit extra for higher tier students where you might be asked to complete a free body diagram, which is a diagram which represents an object and the forces acting on that object. So this question says complete the free body diagram to represent a ball with a resultant force of 10 newtons downwards. Well, at the moment it's got 5 newtons up, so if we want a resultant force of 10 newtons down, then we must have 15 newtons acting downwards, because overall now we'd have 15 minus 5, giving a resultant force of 10 newtons downwards. And this could well be a scale diagram where you'd have to really accurately draw the arrow in an exam. The second question says complete the free body diagram to represent a ball with a resultant force of 0. So this is just checking your understanding. If there's 5 newtons upwards, to get a resultant force of 0, there must be a 5 newtons force downwards. A little bit more tricky work on forces for higher tier students is resolving forces. This question says resolve the force into its horizontal and vertical component. And what this is saying is if this force is acting at an angle, we can break up that force into the horizontal component of that force and the vertical component of that force. So this is an example of what you might need to do. You would draw the force on a graph paper that they would give you in the exam. So draw the arrow to the correct size and scale. They might even put this one on there for you already drawn if you don't have to copy it from a diagram down there. You'd have this arrow and you would need to measure this arrow to calculate your scale. So if we measured it and it was, for example, 8 centimetres, we could look at our scale. So we'd have 5 newtons for every 8 centimetres. And if we divide both sides by 8, that will make this 1 centimetre, because 8 divided by 8 is 1, and that will make this 0.625 newtons. So now you've got your scale, you know that every 1 centimetre equates to 0.625 newtons. You can then draw an accurate horizontal line along the bottom, measure the length of this line, for example 7.5 centimetres, and use the scale to calculate the force. So we multiply each centimetre by 0.625. So 7.5 times 0.625 would give you a force of 4.69 newtons. And vertically, we again would draw a straight line to the top of this force, measure it with a ruler, and then use our scale to calculate the vertical force. So that's taking a force at an angle, resolving the forces into the vertical and horizontal components of that force. And what this is basically saying is, yes, we've got this force at an angle, and this would be like pulling this object here with an upwards force of 1.75 and a sideways force of 4.69 newtons, and that would result in the object moving in this direction with a force of 5 newtons. You could also have a scenario where they ask you to calculate the resultant force when these forces are at angles, so it's not as straightforward as writing a force going to the right and a force going to the left. What you'd need to do is you need to redraw the force arrows, but draw them end to end this time. So if we start off with this one, and at the end of this one we are going to draw the next arrow like so. This gap here is going to give us the size and the direction of the resultant force. So you'd measure it from this point, because this is where we started, up, and you would draw an arrow connecting to that second force that you've put on. So just neaten that up here for you. This arrow here would represent the resultant force, and try and be really accurate, more accurate than I have, to make sure your arrow starts here and meets at the tip of that arrow. You could then be asked to work out the direction of that resultant force. So if we put this vertical line here, you could measure the angle relating to 0 and 180 down here. You could measure that angle using a protractor. That's why you're asked to bring a protractor in the exam. And you could be asked to measure that, for example. So that could be around 40-ish degrees, but you'd need to do it accurately. And you could also be asked to use a scale diagram to calculate the size of that force. So they'd have to give you some values here in order to measure the scale diagram. For example, if they told you that was 5 newtons, you could measure that line in centimetres and work out what each centimetre would be worth in newtons, and then calculate the size of that force. A final example is if you see a situation where the forces are in equilibrium. When forces are in equilibrium, there is no resultant force. So again, you draw the arrows end to end in any order. So let's look at one scenario. You could draw this one here first, and then on the end of it, this one here, and then on the end of it, this one here. And what you'll notice is they form a complete shape without any gaps. And in that case, that's telling you that the object is in equilibrium and there is no resultant force. Doesn't matter what order we put these arrows in. We could start with the longest one first, and then this one, and then this one. If they complete that complete shape with no gaps, then there is no resultant force and the object is in equilibrium. So we'd say the resultant force in this case is 0. In this topic, we need to distinguish between scalar and vector quantities, and the two we're going to focus on are speed and velocity. So the scalar quantity speed has magnitude only, which means it only comes with a size, whereas velocity is classed as a vector because velocity tells you both the size and direction of movement. So for example, with speed, if an object was moving to the right at 3 meters per second, we would just class the speed of the object as 3 meters per second. However, with velocity, we need to indicate the direction that the object is moving in. So what they do in physics is they state which direction is positive and which direction is negative. So for example, a scientist could say, right, let's say that everything moving right is positive and everything moving left is negative. So rather than just writing 3 meters per second, if an object was moving to the right, when we talk about velocity, we'd have to be talking about plus 3 meters per second. So this here just indicates the direction that the object's moving in, hence taking into account direction as well as size. If the object was moving in the opposite direction, then at that same speed, we would then be saying it would be minus 3 meters per second to show it's moving in the opposite direction. So they are both very similar things. They're to do with how quickly an object moves. However, speed just takes into account the size, whereas velocity takes into account direction as well. And then there's another pairing to look at, which are distance and displacement. Displacement is the vector version of distance. Let's have a look at an example. If we have a starting point and an object moves 5 meters and then another 5 meters, the total distance would be 10 meters, 5 plus 5 making 10. However, if we look at the same scenario with displacement, with an object moving 5 meters and moving another 5 meters, because it's returning back to the same original starting point, we would actually say that there was a displacement of 0 meters because they've gone up and come back to this same starting position. So therefore its displacement is 0. So that's the difference between the scalar and vector quantities, speed versus velocity, and distance versus displacement. You need to learn some typical speeds off by heart, so I suggest writing these down. having them on some revision cards to learn them. And these are walking, 1.5 meters per second, running, 3 meters per second, cycling, 6 meters per second. So if you remember walking, running, cycling, each time these are doubling up. These are typical speeds. And then you also need to know for some other modes of transport, which is a car, 25 meters per second, a train, 30 meters per second, and an aeroplane, 250 meters per second. So when they talk about a scenario, for example, a car travelling, and they want you to do some mathematics with that, they might ask you to estimate something about the motion of that car. And if they do, and they haven't given you a speed, then you should be using this typical speed for a car. And the same if they talk about an instant involving, for example, the momentum of a cyclist, and they're talking about estimating momentum. Well, think that the typical speed of cycling is 6 meters per second. So these are just some facts to remember. A couple of other little facts then. Firstly, that the speed of sound is 330 meters per second. And also they just want you to have an understanding that the speed of wind varies. Okay, so sometimes it might be really fast wind, sometimes it would be really slow wind, as you probably know, but that's just one thing that they might ask you to apply your understanding of in the exam. Let's look at some speed equations then. This question says a bee flies at a speed of 10 meters per second for 40 seconds. How far does it travel? So this is applying the equation distance travelled equals speed times time. Distance travelled is measured in meters, speed is measured in meters per second, and time is measured in seconds. So for us to calculate this, we would do 10 times 40, which would give us 400 meters. A little something for higher tier then. Motion in a circle involves constant speed but changing velocity. This is just checking your understanding that speed is scalar and velocity is a vector. So something is travelling at constant speed but changing velocity. Now that must be because it's changing direction. So they'd have the same magnitude all the way around. For example, this ball travelling around in the circle, let's say it was travelling at 10 meters per second, round and around and around and around. Well, yes, it'll have the constant speed as it's travelling around, but because it's constantly changing direction as it's going around the circle, then its velocity is changing. Not the number on the velocity, but just the direction. So it'll always be 10 meters per second, but the velocity will be changing because it's a changing direction and velocity is a vector. With distance time graphs, you need to be very careful that the y-axis says distance and not velocity, and it'll always be over time. So a straight line at an angle like this one here shows that an object is moving at constant speed. A straight line that is horizontal shows that the object is stationary, and here again we would have another constant speed. This line here is much steeper than the third line over here, so it shows that it's moving at a faster speed. It's travelling more distance in a certain amount of time, and this one here a lot shallower gradient, which means it is travelling at a slower speed. You can calculate average speed on a motion graph using the following equation: speed equals distance over time, which is just rearranging that distance travelled equals speed times time equation. If you want to calculate the average speed in the first 10 seconds, you draw a line from 10 up to your graph and then across and read off your distance that it had travelled in 10 seconds. So we know here that within that first 10 seconds it's travelled 40 metres. So if we do 40 divided by 10, we'll get a speed of 4 metres per second. A curved line that gets steeper shows that an object is accelerating. And a curved line that gets shallower shows that an object is decelerating. If you're doing higher T, you'll have to calculate the speed at a particular point on a distance time graph. For example, you might be asked to calculate the speed at 10 seconds. And in this case, you'd have to draw a tangent on the graph at 10 seconds. So here is our 10 seconds going up here, and that's why we've drawn a tangent at this point, which is a straight line as close to the graph as you can get it. You would then calculate the gradient of the tangent by doing the change in y divided by the change in x. So draw a triangle anywhere on that tangent, and we can calculate the x value, the y value, and we remember we always do the y divided by the x. So we do 17 divided by 7.5 to give us 2.3 metres per second. Velocity time graphs. With velocity time graphs, you need to check that the y-axis says velocity and not distance, because that's a different motion graph. With velocity time graphs, a straight line at an angle would show a constant acceleration. A flat line here would show a constant velocity because it's not moving above 40 metres per second in this case. A straight line going downwards at an angle would show constant deceleration. And then here we've got another straight line at a different velocity, so that again shows another constant velocity. You can calculate acceleration on a velocity time graph by calculating the gradient. So essentially we're using the equation acceleration is the change in velocity over time, where v is the final velocity and u is the initial velocity. You'll remember that one because u comes before v in the alphabet, so u is the starting one and v is the final one because that comes after. So if, for example, we said what is the acceleration in the first 10 seconds, we would calculate the gradient of this line here. So we'd have a look and we'd see that we have a velocity change from 0 to 40 in that 10 seconds. So 40, take away 0, so that's your final minus your initial divided by 10, which is your time, should give us the acceleration. So acceleration in this case would be 4 metres per second squared, and have a look at the units for acceleration there. For higher T, you'll also have to calculate the acceleration at a particular point. So if we have a look at this graph here, where the acceleration is changing because it's a curved line rather than a straight line. If, for example, we were to ask for the acceleration at 10 seconds, we would draw a tangent at 10 seconds, determine our values for y and x from that tangent, and do the change in y divided by the change in x. So if we had a look at this, for example, we'd have 17 divided by 7.5 to calculate an acceleration of 2.3 metres per second squared. For higher T, you might actually have to calculate the distance travelled on a velocity time graph. And to do this, you calculate the area under a graph, because essentially you're using the equation distance travelled equals velocity multiplied by time. And if, for example, we're asked to calculate the distance travelled in the first 10 seconds, this would be the area of the graph we are looking at, but we need to calculate the area just under the graph, this shaded region here. So if we take some values from this graph, we're going to calculate the area. So if we do the area of the rectangle and then divide it by 2 to get the area of the triangle, that will be our easiest thing to do. So In the first 10 seconds, the velocity is 40 meters per, goes up to 40 meters per second. So if we do 40 times 10, which is equal to 400, and then we'll divide that by 2 because we've got ourselves a triangle, our distance travelled will be 200 meters. If we were calculating the distance travelled between 10 and 25 seconds, that would be this region here. You wouldn't need to divide by 2 because you're not looking at a triangle, you're looking at a rectangular section. Let's have a look at some acceleration equations then. We've got A equals v minus u over t, where acceleration is in meters per second squared, final velocity in meters per second, initial velocity in meters per second, and time in seconds. So you should remember that u becomes before v in the alphabet. So u is your initial or starting velocity because that comes first, and v is your final velocity because that comes afterwards. Let's have a look at this question. A dog was sat still when he heard someone at the gate. The dog reached the gate in 2 seconds, so that is going to be our time, and was travelling at 6 meters per second when he reached the gate. So this is our final velocity. Calculate the acceleration of the dog. Calculate A. So the other bit we need is u. We need the initial velocity, so you need to read the question very carefully again. It says a dog was sat still. So this here implies that the dog was stationary, therefore that is our starting velocity, which was 0. So then we can do 6 minus 0, so v minus u, divided by the time, which is 2, and our acceleration would be 3 meters per second squared. Then we've got another acceleration equation, which is v squared minus u squared equals 2as. Again, acceleration, final velocity, initial velocity. S in this equation is distance. And let's have a look at this practice question. It says an aeroplane accelerated at 10 meters per second squared from 100 meters per second to 200 meters per second. Calculate the distance travelled by the plane while accelerating. So this time we're rearranging this equation to calculate S. You might have to rearrange the calculation to calculate any one of U, V, or A. So let's have a look at it then. 200 squared is our final velocity here. U is our initial velocity of 100 meters per second. So we square that, and then that is equal to 2, which is our constant in our equation, multiplied by acceleration of 10, multiplied by s. So if we simplify this, we're saying that 30,000 equals 20 times s, because those two make 30,000, those two make 20, and then rearranging it to 30,000 divided by 20 equals s. So s is equal to 15,000 meters. So let's consider the motion of this skydiver who's just jumped out of a plane. All objects falling towards the Earth will be accelerating at 9.8 meters per second squared. So this skydiver will have the force of weight accelerating him towards the Earth. And as he initially jumps out of the plane, he'll also have a very small air resistance acting in the opposite direction, which is shown by a smaller arrow. So here we've got a scenario where weight is larger than air resistance, and therefore the motion will be acceleration. So he's accelerating towards the Earth. And then as speed increases, so as he accelerates, then air resistance will also increase until you get to a point where the air resistance will balance out the weight, shown by the same size arrows here. And in this case, he will be not accelerating anymore, but he would have reached a constant speed. And when he's falling, because he's falling through a fluid, we call this constant speed a terminal velocity. So fluids are liquids and airs. And air, if you are falling through a liquid or a gas like air, then you are said to reach a terminal velocity, which is your final velocity. You can't go any faster than that at the point that your weight matches the air resistance, is balanced by the air resistance. So then the parachutist will deploy a parachute, and at this point there is a much larger air resistance and a smaller weight, which will cause a deceleration. And then finally, the air resistance and the weight will balance each other out again because he'll slow down and air resistance will decrease. So those two will balance out again and he will reach a new constant speed and therefore, because he's falling, a new terminal velocity. Forces, accelerations and Newton's laws of motion. Let's have a look at Newton's first law. This is all to do with the resultant forces acting on an object. And the first part of it says that if the resultant force acting on an object is 0 and the object is stationary, then it remains stationary. So for this vehicle here, you've got the weight acting downwards, a normal contact force acting upwards. There's no air resistance or thrust here, so these two forces are balanced. The object is stationary and there's no resultant force, which means it's just going to stay stationary. In the second example, if the resultant force acting on an object is 0 and the object is moving, the object continues to move at the same speed and in the same direction. So the object continues to move at the same velocity. So because velocity takes into account speed and direction, if the resultant force of this car is 0, because here we've got your normal contact force, your weight, and the thrust and the air resistance are balanced out, this car is moving and it has no resultant force, then the object will continue to move at the same velocity. So have a look very carefully to see whether the object is already stationary or whether it's already moving. Because if it's stationary and there's no resultant force, it will stay stationary. If the object's moving and there's no resultant force, it will just continue to move at the same velocity. The velocity of an object, so taking into account the size of the speed or the direction of the object, will only change if there is a resultant force acting on the object. So let's say we increased this thrust here, so we had a greater forward force compared to our air resistance. Now we have unbalanced forces. We will have a resultant force overall acting in this direction here because of this increased thrust. And then now we'll be changing velocity. We'll be changing the speed, not necessarily the direction, but the speed of the object as it will accelerate forwards. Newton's second law says the acceleration of an object is proportional to the resultant force acting on an object and inversely proportional to the mass of an object. This links to the equation F equals ma, or force equals mass times acceleration. Force is measured in newtons, mass in kilograms, and acceleration in meters per second square. So look out for this symbol here. This shows that acceleration is proportional to the force, and you might also see it in a sketch graph of acceleration against force as well. So for example, if we had force and acceleration, they would be directly proportional. And this means as force increases, acceleration increases. And in the other relationship, acceleration is inversely proportional to mass. And this means as mass increases, acceleration decreases. So inverse proportion means as one thing gets bigger, the other thing gets smaller. And that's where you'll see a graph, if we put mass against acceleration, would look a little bit like this. As mass increases, acceleration decreases. Let's have a look at an example. A boy kicked a 500-gram stationary ball with a force of 20 newtons. Calculate the acceleration of the ball. Well, first of all, let's look at converting the grams into kilograms. So 500 divided by 1,000 would give you 0.5 kilograms. So do look out for those kind of things in the exam. The equation we're using is force equals mass times acceleration. That's one that links to Newton's second law. And we'll put the numbers in that we've got. So 20 newtons is the force, 0.5 kilograms is the mass. So if we rearrange this, acceleration would be equal to 20 divided by 0.5, which will give us an acceleration of 40 meters per second squared. For height here, you also need to be aware of the meaning of inertia, and that is the tendency of objects to continue in their state of rest or of uniform motion. So if objects are already stationary, they'll in the state of inertia, they'll remain stationary, or if they're already moving, they'll continue moving in a uniform motion. So looking at our F equals ma equation, if we rearrange F equals ma, we get mass equals force divided by acceleration. And this type of mass, within this equation, once you've worked out force divided by acceleration to calculate your mass, when you've calculated mass this way, this is called inertial mass. And it is a measure of how difficult it is to change the velocity of an object. So acceleration is changing velocity, force, the force you need to change that velocity. So that, when you calculate mass, is called inertial mass. And it is defined as the ratio of force over acceleration. So that's shown in this F equals ma equation. Inertial mass is calculated by force divided by acceleration. So actually, scientists haven't found that this inertial mass is any different in terms of size to any other way you'll calculate mass, but theoretically, this particular mass here that you calculate by doing force divided by acceleration has got this special name of inertial mass. Newton's third law says that whenever two objects interact, they have to be two different objects. Whenever two different objects interact, the forces they exert on each other are equal and opposite. So this is that equal and opposite law. So for example, when you sit this mug on a table, the mug will exert a force on the table, and the table will exert a force on the mug that is equal in size and opposite in direction. When you press this button here, one object is the finger, the other object is the button. The finger will press the button with a force and apply a force to the button, and the button will apply a force in the opposite direction that is equal in size and, as I said, opposite in direction. Momentum. Momentum is equal to mass times velocity. Momentum is measured in kilogram meters per second, which is the unit for mass multiplied by the unit for velocity. So you just write the two next to each other. Mass is measured in kilograms and velocity is measured in meters per second. The conservation of momentum says that the total momentum before an event is equal to the total momentum after the event. Now let's look through some worked examples for momentum calculations. The first one that we'll do is a collision. In this question says stone 1 slides to the right and hits the stationary stone. After the collision, it kept moving in the same direction at 0.5 meters per second. Calculate the speed with which stone 2 moves to the right. So initially the speed of this stone 1 was 2 meters per second and its mass is 20 kilograms. That was moving to the right and it hits this stationary stone, stone 2, that is stationary. So this tells us that it has a speed of 0 meters per second and it also has a mass of 20 kilograms. So the momentum of stone 1 before is 20 multiplied by 2 because mass times velocity is momentum. So the momentum before of stone 1 is 40 kilogram meters per second. And the momentum before of stone 2 is 20 times 0, which is 0 kilograms meters per second. So if we add those two together, the total momentum before would be 40 plus 0, which is 40 kilogram meters per second. So all we've done is before the collision, we've worked out the momentum of stone 1, that was 40, the momentum of stone 2, that was 0. Add them together and we get the total momentum of the whole system before the collision. So the total momentum after, because of conservation of momentum, must also equal 40 kilograms meters per second. That's not given to us. That's just through our knowledge of the conservation of momentum, that total momentum before is equal to total momentum after. So now we can calculate the momentum of stone 1 after, because in the question it told us that it kept moving in the same direction, but this time at 0.5 meters per second. It's got the same mass, so it's still a 20 kilogram stone. So this time its momentum is 0.5 times 20. So now its momentum is 10 kilograms meters per second. So that's momentum of stone 1. So if we know the momentum afterwards should be equal to 40, we know that 10 kilograms meters per second of that is taken up by stone 1. So we know that momentum of stone 2 must be 30 kilogram meters per second, because 40 minus 10 is equal to 30 kilogram meters per second. So stone 2, we can calculate the speed or velocity with which it moved to the right, because momentum equals mass times velocity rearranged will give us momentum divided by mass equals velocity. So if we take the momentum of 30, divide by the mass of the stone, which is also 20, this tells us that stone 2 moved away with a velocity of 1.5 meters per second. Now let's look at an explosion example. This one says a cannonball with a mass of 5 kilograms is fired from a 100 kilogram cannon at a speed of 150 meters per second. And the question says calculate the velocity of the cannon as it recoils in the opposite direction. So when the cannonball is fired out, that will go in this direction, and the cannon itself will recoil in the reverse direction. So we've got the total momentum before is 0 kilogram meters per second. And that is because before the explosion, everything is stationary. The cannon is stationary and the cannonball inside is stationary. So nice easy one, we know the momentum before is going to be 0. That means the momentum afterwards must also equal 0 because the momentum is conserved. So we can work out the momentum of the ball from the information in the question, because we have been told it has a mass of 5 kilograms and it travels with the speed of 150 meters per second. So mass times velocity is equal to 750 kilograms meters per second. And you'll notice the plus here, because we're talking about velocities. I have decided that going right is a plus direction, and going in the opposite direction we'll assign that a minus. So the ball is moving to the right, so we're going to describe it as plus 750 kilograms meters per second, and the recoil of the cannon will be a minus number. So the momentum of the cannon afterwards is, we know, must be minus 750. And we know that because total momentum afterwards must be equal to 0 because of the conservation of momentum. And if the ball has gone forward plus 750 kilogram meters per second, then to get to 0, the momentum of the cannon afterwards must be minus 750, because if you add those two together, you get a total momentum afterwards of 0 kilogram meters per second. Okay, so that's how you get to that bit. So we know the momentum of the cannon afterwards is minus 750 kilogram meters per second. And if we rearrange momentum equation, momentum divided by mass is the velocity. In the question, they've told us the mass of the cannon is 100 kilograms. So if we rearrange that, we will get minus 750 divided by 100 to give us a velocity of minus 7.5 meters per second. And again, the minus is there just because velocity is a vector, so it shows us or gives us an indication of the direction that that cannon is moving in. Electromagnetic waves. Electromagnetic waves are transverse and they all travel at the same speed, which is 3 times 10 to the 8 meters per second. You need to know the order of electromagnetic waves in the spectrum. So this is shown in the order from the longest wavelength to the shortest wavelength. And the order will be radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. And this is also the order from the lowest frequency wave to the highest frequency wave. So down this end of the spectrum, you'd get the longest wavelength waves, and at this end of the spectrum, the shortest wavelength, high frequency, high energy waves. Don't be put off in the exam if they ask you to list them in the other way, from shortest wavelength to longest, from gamma through to radio waves. In the middle, the visible light is split up into red, orange, yellow, green, blue, indigo, and violet. So if you were to split what we call white light, you would see this spectrum of colours. So you need to know that order, Roy, G, Biv. And you'll see that the red is closest to the infrared light in the spectrum, and the violet is closest to the ultraviolet. And this is why lots of things emitting ultraviolet will also emit parts of the visible light spectrum, and you'll see them as violet. Things that emit infrared radiation will also often emit part of the visible light of the spectrum, so they will come through to your eyes as red. Our eyes detect only visible light. So there are lots of other waves of electromagnetic radiation, but our eyes, as an organ, only detect visible light. Some animals, for example, can see into ultraviolet light, but our eyes only see visible light. The high frequency, short wavelength, high energy end of the spectrum can have hazard effects on human body tissue. So these are UV, X-rays, and gamma rays. For example, ultraviolet light can prematurely age the skin and cause skin cancer. And it's important in the exam, if you're talking about ultraviolet, that you must link this directly to skin cancer and not just generally write cancer. X-rays and gamma rays are both ionizing. That means they can strip electrons off of atoms. So they can cause gene mutations and also cancer. And we could be a bit more general there because they can cause different forms of cancer. So these ones are particularly dangerous, and ultraviolet we should try and avoid as much as possible as well through sun creams and wearing appropriate clothing in the sunshine. Radiation dose is measured in a unit called sieverts, and it's a measure of the risk of harm resulting from radiation exposure. And it's useful in hospitals because there will be doctors and nurses and other staff members that work in areas where there are, for example, lots of X-rays or gamma rays, or patients might need to have lots of X-rays or treatment involving gamma rays, and you need to know how the radiation dose is going to affect you and what the risk of harm is. So radiation dose takes into account two things. It takes into account the type of radiation that you're exposed to and the size of the dose that you get. Okay, so you need to bear in mind that radiation dose takes into account the type and the size of radiation that you are exposed to, but you don't have to remember that the units are sieverts. So you might see sieverts in a question when they're talking about dose, but you don't have to remember those units. So let's look at the uses of some of these electromagnetic waves. Radio waves are used for TV and radio communications. Microwaves are used for satellite communications or for cooking food. And because it's a spectrum, it will be a different wavelength used for cooking food compared to the wavelength that you would use to communicate with satellites. Infrared radiation, that's used in electrical heaters, cooking food. So both of these two will obviously glow red because it's close to the red part of the visible light spectrum as well. And also infrared cameras, which will detect infrared light rather than visible light. So the heat or infrared coming off of objects will be detected by those cameras. Visible light used for fibre optic communications. Ultraviolet light used for things such as tanning beds or energy efficient lamps using ultraviolet. X-rays, medical imaging, and gamma rays, medical treatment. So gamma rays are often used to kill cancer cells, for example. For higher T, you need to know a little bit more about how radio waves are transmitted. So for TV and radio communications, radio waves can be produced from alternating current. So be able to watch the TV or listen to the radio when it is communicated via radio waves. You have a transmitter and a receiver. The transmitter will produce a radio wave. Okay, so alternating current, which I've abbreviated AC here. So alternating current in the transmitter produces a radio wave, and that receiver absorbs the radio wave, and then this generates its own alternating current, which is at the same frequency as the radio wave. So frequency, remember, is measured in hertz. So whatever the frequency of the radio wave is, that will produce an alternating current of the same frequency inside the receiver. All electromagnetic waves change direction when they enter a different medium. So you can think of this as a different material. So this is called refraction. So refraction is when waves change direction when they enter a different medium. So here you've got the medium of air, and here's your barrier, and the other side you've got glass. So air and then glass. So this wave is coming in here, hitting the glass, and is bending. So rather than carrying on this same direction that it was going through first of all, it's bending and changing direction to head out this way. And if it enters a denser medium, it will bend towards the normal, which is in the case of this diagram here. So air is less dense than glass, so the wave is heading in this direction. It's going from the less dense air to the more dense glass, so it bends towards the normal. The normal is this imaginary line here, this dotted line. This is the normal line, and this is drawn at 90 degrees to the surface. So here at the boundary that it joins here, this angle here is 90 degrees, and that is the normal line, or you could draw the 90-degree angle there, either or. It is 90 degrees to the surface. So rather than carrying straight on here, you can see this is bending towards the normal, so this angle will be a lot larger than this angle here. A little bit more refraction for higher tier. Refraction occurs as the wave slows down. So you might be asked to explain why refraction happens, okay? Because it slows down as it enters the denser medium. If it was going at the same speed, it would travel straight on like so, but because it slows down, it bends towards the normal in this direction. You also need to complete the diagram to show the waves moving from a less dense to a more dense medium, but you might have to show this as wave fronts, which are shown here. So these are wave fronts, and what you can imagine these are, if I draw a wave for you now, like so, if we were to look at the top of the wave and look at these peaks, these would be the wave fronts moving through the water. So it would look a little bit like this for this wave here. So if you measure the distance between the wave fronts, you're getting the wavelength because it's the distance between two peaks. So as this wave is entering the more dense medium, shown by this grey area over here, they will change direction. So if we draw a normal line onto this diagram here at 90 degrees to this change in medium line here, the waves will bend towards the normal. So at the moment they're coming in this direction. Rather than going straight on, they're going to bend towards the normal like so, and therefore if we draw the wave fronts the other side, we'll draw them continuing here along the bottom and then show them changing direction. So here we've got our new wave fronts in a different direction, and also what you'll see is the wave fronts are closer together because the waves are slowing down. Here's another example. This time you'll notice here is the boundary between the less dense and the more dense medium. This is the more dense, this is the less dense. So here's the boundary, but this time you can see the waves are actually travelling at 90 degrees to the boundary, so they're travelling along the normal, and therefore if they were to continue through that boundary to the side, they wouldn't change direction because they're travelling along the normal. However, they would still slow down, so you would still need to draw your wave fronts closer together, but they don't need a change of direction if they travel along the normal. The motor effect. When a current flows through a conducting wire, a magnetic field is produced around the wire. So let's have a look at the right-hand thumb rule. You can use your thumb to show the direction of current, and for example, if your thumb is pointing upwards, the direction of current will be up from positive to negative, and your fingers will show the direction of the magnetic field. So you can imagine your fingers pointing inwards like so, and importantly it has to be your right hand that you use to do this. So if you make a fist and a thumb with your right hand, the thumb would show the direction of current, so in this case we could do positive to negative, and your fingers would show the direction of the field lines. If the current is flowing in the other direction from positive to negative, you simply turn your thumb upside down and that will show you the direction of the field lines depending on where your fingers curl into your palm. So if we use that rule on this wire, you've got the wire travelling up here from positive to negative, the current would be upwards, so we could point our thumb up like shown in the diagram here, and the magnetic field lines would curl round into our palm like so. So we can draw the arrows on the field line going in that direction. The magnetic field line is stronger closest to the wire, and you can see that because the field lines are closer together, so they're stronger closer to the wire, and as they get out they would just get further apart and weaker. And if you increase the current flowing through the wire, the strength of the magnetic field also increases. A coil of wire is called a solenoid. So this would be a solenoid. And a solenoid, if it has a current flowing through it, will produce a magnetic field. So very similar to the bar magnet, you've got your north and your south, and the field lines always go from north to south. The magnetic field line inside a solenoid is strong and uniform. You can see that by these straight lines of the field lines inside. They're really close together, so the magnetic field is strong and uniform because there are straight lines of field lines going through. If you add an iron core, you increase the strength of the magnetic field. So if you put a core inside there, and a solenoid with an iron core is called an electromagnet. So if you were to put an iron core inside that coil, we could now call that an electromagnet. Electromagnets are useful because when an electromagnet is switched off, it loses its magnetism. So if we'd switch these off now, it would drop the nails, and this makes it useful for picking up objects and dropping them somewhere else. So for example, on a scrapyard, they're used to pick up magnetic objects and drop them somewhere else in the scrapyard. A little bit on the motor effect for higher tier. When a conductor carrying a current is placed inside a magnetic field, the magnet producing the magnetic field and the conductor exert a force on each other. This is called the motor effect. So if this wire here was carrying a current, if we were to place this inside the magnetic field of this bar magnet, the magnet and the wire would both exert a force on each other, because don't forget, this wire, because it's carrying current, will also be producing its own magnetic field, and that's why they produce a force on each other. So we can use Fleming's left-hand rule to work out the direction of motion that a wire would experience if placed in a magnetic field. So when you do the Fleming's left-hand rule, you must use your left hand, which is different to the right-hand grip rule that we looked at earlier. Your thumb, your first finger and your second finger must all be placed at right angles to each other. And your first finger you should put in the direction of the magnetic field, which will always be from north to south. If you set that one up first, it's a little easier. Your second finger will then go in the direction of current, which always goes from positive to negative. And if you set these two up, then automatically your thumb will be pointing in the direction of the motion, which is going to tell you which way the wire moves. So for example, it might move up or down, or maybe left or right, depending on which system you are looking at. So if we look at this example, this is a simple motor. You've got some magnets here, a north and a south of two magnets, and you have a wire going in between. So these magnets are producing a magnetic field. You're placing a wire carrying current in the magnetic field from positive to negative, so that will experience a force. So the first finger you point north to south, so you'd point the first finger in this direction. You would point your second finger in the direction of current, so that will be from positive to negative. And when you do that, automatically your thumb should now be pointing downwards, and that will tell you that the wire moves down. If it's not pointing downwards, you may be using the wrong hand. You've got to use the left hand for Fleming's left-hand rule. So when you have a coil of wire carrying a current in a magnetic field, it will rotate. And this is the basis of an electric motor. So if we apply Fleming's left-hand rule to each side of the coil, you can see which side goes up and which side goes down. So when I say each side, have a look at this side of the wire and have a look at this side of the wire, and you work out which one goes up and which one goes down. In both cases, the direction of the magnetic field is going to be from north to south. But on this side of the wire, because you've got positive going to negative, so the current goes along here, all the way down, round, and over here. Because we've got that direction, on this wire, the direction of the current is like so, and on this wire, the direction of the current is in the opposite direction. So if you apply Fleming's left-hand rule to that, you will see that this side will be going up, and this side will be going down. And this will tell you if the motor spins clockwise or anti-clockwise. So in this case, if this side of the motor goes up, this side goes down, then we must have a clockwise motion on the motor. However, we want a motor to keep on spinning, and if we just did this, we would end up with this side being over here and that side being on the opposite side, and it would just stop. But we need it to keep spinning and spinning and spinning, and this is where this part of the motor becomes important. This is a split ring commutator, this part here, and this switches the direction of the current every half turn so that the coil of wire keeps spinning. So we said that this one would go up, this one would go down, and there would be a clockwise motion. However, that would just stop if it wasn't for the split ring commutator. This switches the direction of current, so then this side will go down, this side will go up, and it will just keep on spinning round and around and around, which provides the basis of our electric motor. Extra equation for higher tier is force is equal to magnetic flux density multiplied by current multiplied by the length of wire. So the force that the wire experiences is equal to essentially the strength of the magnetic field multiplied by the current flowing through the wire multiplied by the length of the wire that is inside that magnetic field. So FBIL is for short. So force is measured in newtons. Magnetic flux density is the B part, and that's measured in Teslas, capital T. Current I is measured in amps, and length L is measured in meters. So a quick example might be something like calculate the force on a 20 centimetre wire with a 3 amp current flowing through it in a magnetic field with a magnetic flux density of 0.4 Teslas. So using FBIL, we first convert our 20 centimetres into meters, and then we put our numbers in. Force is equal to 0.4 Tesla times 3 amps times 0.2 meters, which would be equal to 0.24 newtons.